digital dentistry and artificial intelligence. Before I start the lecture, I would like to remind you that in order to get credits for the lecture, you must fill in the feedback form in the Moodle platform after the lecture. Currently, we live in times of data explosion. A large amount of data is being generated all over the world. It's estimated that it's about 1/3 of 6 billion of data a day. And what is a 6 billion? It's 1 billion terabytes, so 10 to the power of 21 bytes just in 3 days. You can have a look at the diagram presenting the amount of data growing exponentially. So this is 2024, this is 2025, and the graph starts from just 2010. So it's 60-fold increase between 2010 and 2023. And imagine that before that, it's all the history of mankind. So we are living in the times where data is generated continuously, and in a way, it's not possible anymore for a human being to follow all the information. So this is the digital 21st century, and the new technologies change our society. This is AI, cloud computing, big data analytics, neural networks, deep learning. So what is the role of big data, of AI in dentistry, in radiology? What are the capabilities of this technology? Is it a new revolution? So what is digital dentistry? It's a very broad and not so very new concept of application of digital solutions in dentistry. So far, we base mostly on digital evaluation of images. So these can be the images obtained in our department, like this CBCT machine, generating two-dimensional images, panoramics, and cephalometrics, as well as three-dimensional cone beam CT. It's digital images from intraoral and extraoral scanning that you always also practice during the classes in our faculty. It's images from optical coherence tomography or from confocal scanning microscopy. When we take a look at the table with use of data in, for example, in prosthodontics, AI is used on intraoral scanner information, also on optical images, for example, of abutments, and intraoral optical images. In oral surgery and oral medicine, it's confocal laser endomicroscopy images, intraoral optical images, and optical coherence tomography images. And of course, it's radiography, just like this digital panoramic. So right now, majority of applications of artificial intelligence in digital dentistry concern radiology. And this is the topic of my lecture, to discuss the role of AI in imaging. What is artificial intelligence? This is a machine that mimics a cognitive function of human mind, and it's also a branch of computer science dedicated to the development of computer algorithms to accomplish tasks traditionally associated with human intelligence. But artificial intelligence is not a new term. What does it mean, a new term? Well, again, in contrast with the whole history of humankind, this is a kind of new term. But if we have a look at the first attempts at artificial intelligence back in 1950s, it's very, very short time, not very long time ago in comparison with the whole history. But in comparison with the development of computer science, it's definitely an old term. So already in 1950s, Alan Turing proposed a test called initially the imitation game. This is a test of a machine's ability to exhibit intelligent behavior equivalent to, or at least indistinguishable from, that of a human. Turing proposed that a human evaluator would judge language conversations between a human and a machine designed to generate human-like responses. Of course, at that time, voice generation was not available like it is nowadays, so the conversation was being held by a computer keyboard. If the evaluator cannot reliably tell the machine from the human, the machine is said to have passed the test. The test results do not depend on the machine's ability to give correct answers to questions, only how closely the answers would resemble those of a human being. So already in 1950, Alan Turing expected that finally the machines would be able to pass the test successfully, and he estimated that around 2,000 machines with capacity of 10 to the power of 9 bit would be able to fool 30% of judges during just a 5-minute test. First papers on artificial intelligence also appeared in the 1950s, but the concept of artificial intelligence was very, very simple at that time. However, since then, we have experienced tremendous progress in the field of artificial intelligence, and what we use in radiology, it's based more on machine learning as a subset of artificial intelligence and more refined deep learning. So machine learning is when machines learning begins to flourish, and deep learning, it's breakthrough in AI boom. AI, it's the development of knowledge and application areas until, let's say, 1980s, then between 1980s and 2010, image processing and detection, and since 2010, focus is placed on learning from raw images and the use of neural networks. So how can a machine learn? The machine has to have some data input, then processed, by algorithms and then produces an output. It's based on the creation of algorithms that can learn from the data and make predictions on the data. And the first step of training a machine is feeding it with some kind of training data set. So generally, machine learning is about how to solve specific tasks based on case studies. In a very simple form, it's the input, in our case it's medical images, then it's feature extraction and definition, then training and classification, and following classification with the use of feature 1 and feature 2, the output is given by the machine. You can see the dots of different colors, which means that by now the machines are not 100% specific and 100% sensitive, but the same concerns humans. Machine learning in 1980s focused on realizing artificial intelligence in speech recognition, image recognition, dialogue, and in autonomic cars. And nowadays, you face AI in your own mobile phone with face recognition. If you call to book a taxi and you don't book via an app, instead of a human, you can encounter an automated boat that takes your order. How to teach a machine. So there are different types of machine learning. There is supervised learning when you have input variables and an output variable, and you use an algorithm to learn the mapping function from the input to output. In unsupervised learning, the machine gets just the input data and no corresponding output variables. In semi-supervised learning, it's both. So a part is labeled with input and output data, and some it's only input data. And reinforcement learning, where is no need labeling output, input pairs, but the machine learns from the environment. And neural networks, artificial neural networks, are based on natural neural networks. So this is, you know, from human anatomy, human physiology. When you step on something which is sharp, this is a stimulus. And the neurons in your body will pass the information all the way to the brain. And it's only the brain that perceives the feeling of pain. And of course, the reaction is the opposite direction. Also, the neurons serve as transmitters of information from the brain. So if you're feeling pain, you understand that you stepped on something sharp, and you will have to remove your foot in order to avoid further injury. So this is very simple example. And the most simple neural network, artificial, has less abilities than a biological neural network. However, together with other artificial neurons, it creates larger networks. So again, you've got an input, you've got a summand block, and you've got an output. Deep learning is based on artificial neural networks, which are mathematical models inspired by and modeled on biological neural networks. Artificial neural networks are able to model and process nonlinear relationships between inputs and outputs. An artificial neural network consists of input layer, hidden layer or layers, and output layer. And the layers in the hidden layers are the nodes between the input and the output layer. This is a very simple example of an artificial neural network. If you go to any lecture on AI, most probably the lecturer will use an apple, maybe an apple and a pear, to explain this most simple neural network. So there is an image of an apple, and there is input layer, hidden layer, output layer, and the output from evaluation by the machine is classification, an apple or not an apple if it's a pear. Deep learning is combining artificial neurons and connecting layers of artificial neurons with mathematical operations to create a network that can solve certain tasks such as image classification in radiology. And the more layers between the input and the output are one, the more precise results are. So the term deep refers to the number of hidden network layers used gradually to extract information from the data. So you can see how many solutions, how many connections there are with more complicated neural networks. And convolutional neural networks are used to analyze patterns. So this is, for example, first edges, then texture, then some pattern, object parts, and finally identification of full objects. And this is exactly what human brain does when looking at any radiographic image. We first have to detect the edges and tell if it's well-defined or ill-defined, what's the texture, if it's homogeneous or heterogeneous, some kind of repeating pattern, everything you've been learning during this semester, like ground glass, for example, or snowstorm patterns, and then you are able to classify it as some kind of pathology. Convolution is a formally defined mathematical operation using integrals, and the convolution operation is a matrix transformation of fragments of a photo, which aims to extract information about specific features of the image. And examples of use in everyday life, it's detection of faces on photographs and mobile phones, it's detection of voice commands by virtual assistant, and it's also autonomic cars. However, AI is still tricked. It's not so perfect so far, hopefully. And how to distinguish between a dog with big brown eyes and nice, cute brown nose, and a cupcake with some berries. And another example, we've got also dogs, but we've got also cleaning devices. And as far as neural networks are concerned, they are arranged in networks by different names and by different architecture. And of course, we radiologists, we do not do that on our own. We rely on our colleagues from computer sciences. So these are different structures of the networks, and some of them, they are already commercialized, like UNet. How does this classification work? Well, so this is classification as a cat, and classification and localization, and example, a single object, and in case of multiple objects, object detection, so a dog, a cat, a dog, and then also segmentation of the shape of these animals. So exactly what we do regarding radiological images. So here's example of object detection in panoramic radiography and intraoral detection of individual teeth. And image segmentation regarding, for example, pulp chambers and root canals, prediction of caries, and segmentation of, for example, masseter muscle, which means that not only images from radiography can serve as basis for AI analysis, but also ultrasound images. And in order to train an algorithm, we have to feed it with a lot of images. So it can be thousands of images, and the more images are input in the machine, the more reliable output, the more reliable result of validation. Having a look at applications in maxillofacial radiology, already sometimes back in 1976, there were some papers on artificial intelligence in maxillofacial radiology, but they were rather scarce, and suddenly in the recent years, it's again exponential growth of papers on the subject. The applications in maxillofacial radiology include radioanatomy evaluations, pathology evaluations, CBCT artifacts, landmark detection and segmentation, use in endodontics, use in orthodontics as prediction of the movements of teeth during scheduled planned treatments. So this is one of our papers on automatic feature segmentation in dental variapical radiographs. We use this kind of network UNet architecture with multiple layers arranged like a U. And this UNet was tested on different tasks. One of them, it's dental condition segmentations on periapical radiographs, and it's, for example, dental caries, then it's segmentation of crown, it's segmentation, like in this case of prosthetic crown, segmentation of dental pulp, pulp chamber and root canals, segmentation of fillings, segmentation of root canal fillings, and finally segmentation of periapical lesions. So this means that the algorithm can be used for diagnostics, well, maybe not necessarily for diagnostics, but for finding lesions, and then, if not diagnosed, at least highlighted for a human observer. And the algorithms of artificial intelligence are getting better and better, with sensitivity of this algorithm, for example, for dental crowns, prosthetic crowns, it's 100%, for dental pulp segmentation, 97%, also 100% sensitivity for finding root canal fillings, and it's slightly lower for caries lesions, but it's absolutely obvious because caries is difficult also for human observers. So where was AI applied in different tasks in digital radiology regarding radiographic images? So, for example, in tooth numbering in panoramics, in tooth numbering in periapical radiographs, in bite-wing radiographs, in tooth numbering in cone beam CT, and you can see that in this paper, the accuracy of numbering the teeth was 88%. Well, we found out in a study conducted in our department that AI algorithms are diagnostic accuracy is lower in case of patients with mixed dentition, and the algorithms are tricked mostly by deciduous teeth with physiological root resorption. They do not recognize the teeth or they number them incorrectly. Then algorithms of artificial intelligence can be used for assessment of root morphology, like in this case for first molar in panoramic for detection of this extra supernumerary roots. And what's interesting about these papers, it's not only the sensitivity and specificity, but it's also the time for analysis. So the time for analysis is far shorter than that of human beings. Caries detection also applies here in case of intraoral periapical bite-wing radiographs and CBCT radiographs. And we had a look at the use of artificial intelligence in radiological diagnosis and detection of dental caries in 2021. We had a look at several studies included in our research starting from 2008 until the year of publication. They relied on bite wings, on periapicals, one study on cone beam CT, and one study on panoramic radiograph. And I would like to remind you that panoramic radiographs are not radiographs of choice in detection of caries. But of course, if a radiograph is taken due to other indications, you must report dental caries as well. So all these studies used different AI models, and they also presented different outcome metrics, which means that the studies on AI are not standardized currently. This is another from our studies on evaluation of a decision support system developed with deep learning approach for detecting dental caries with CBCT imaging. And this is the interface for evaluation, which is also commercialized. And this is an image from CBCT that provided an overall view, and then the information about condition of individual teeth presented as a chart. And caries is detected and mapped in color in individual images. So this is definitely helpful for a human observer when caries is automatically detected. And another step for use of AI in more complicated tasks is evaluation of AI for detecting vertical root fractures on panoramic radiography. Also for periapical pathology detection, several papers. Next, for periodontal bone loss with highlighting of the areas of the bone loss in the resultant radiographs with maps in color. For mandibular canal detection, and in fact, these algorithms are already included in majority of software, which is fitted together with the X-ray or CBCT machines. The next step is the use of artificial intelligence in detection of impacted teeth, and this especially concerns third molars, and together with highlighting the course of mandibular nerve canal, it serves as the prediction of the complexity of extraction of such a molar. Deep learning-based prediction of extraction difficulty for mandibular models also was quite well in assessment, and the proposed accuracy was around 80 to 90%. The next task, which is also complicated for human observers, is detection of cysts and tumors. And the major obstacle for training machines into diagnosis of cysts and tumors is insufficient amount of data, insufficient volume of the database for training, as some of the cysts, some of the tumors are really infrequent. So it's difficult to get a lot of examples for the machines to learn. It's much more easy to teach the machine to detect caries or periapical lesions because there are thousands, millions of images available for training sets. Nowadays, AI is also used in implant detection and classification. The solutions based on AI are also included in the software for dedicated software for CBCT and help in planning implant. Of course, again, it's possible for human to adjust the implant, the virtual implant, on the basis of the prediction from AI. Nowadays, cone beams tomography is also analyzed by AI solutions for orthodontics. So one of these solutions is segmentation of the images of individual teeth and then proposing prediction of the course of treatment, especially with aligners. Cephalometric analysis is quite tedious and time-consuming task, so also AI-based algorithms are trained to perform the analysis instead of humans. Another topic in orthodontics is the assessment of cervical vertebra for age estimation. And once again, it's time-consuming and it's repeatable for a human, so it may be a boring task. And this is where AI is perfect because AI is never tired. AI can work 24/7, and AI can prepare the images with evaluation of age estimation on the basis of cervical vertebra visible in lateral cephalometric radiographs. Another use of AI for segmentation is segmentation of upper respiratory tract, and this is useful in evaluation of patients with sleep apnea. I have already mentioned that AI-based solutions, deep learning solutions, can be applied not only to data generated from images based on X-rays, but also on other imaging techniques. I showed you an example of ultrasound, but this is the segmentation of the condyle of the mandible and the lateral pterygoid muscle from MRI images. A deep learning algorithm can be used also for analysis of photographs, not digital radiographs, but digital photographs, for example, in this case, from oral cavity, like oral lichen planus lesions. And this is the analysis, the photography, the lesion, and the AI algorithm marking the lesion on the photograph, and another lesion in this patient marked by AI. Deep convolutional neural network algorithm was also used for automatic segmentation of oral, potentially malignant disorders and oral cancers. And this is an example. Of course, this is a pretty easy example because this patient has a massive infiltration by cancer. So, of course, it's very easy to detect also by human. But this serves as training model for the patient, for the AI software. But in this case, it's smaller lesions on the tongue and also on buccal mucosa, and the lesions are highlighted by the software. Another example highlighting the extent of the lesions in the oral cavity. So taking a look at all these images, we might agree with George Hinton, the father of AI, who already in 2016 said that radiologists were like this coyote hanging over the cliff. If you like cartoons, you remember that this Speedy Gonzales, this ostrich, it used to threaten the coyote, and then the coyote that wanted to trap the coyote wanted to catch the ostrich, but it always failed. So in the cartoons, the gravity laws did not apply. So this coyote is hanging over the cliff, but in the cartoon, it will hang there for a moment, for a few seconds before falling. So Jeffrey Hinton said that we are like the coyote, we radiologists. We are already over the edge of the cliff, but we do not realize that we will soon fall. And oral radiologists and other radiologists will not be useful anymore. So what did I do? I asked ChatGPT, who's an oral radiologist, and then I asked ChatGPT whether AI would replace oral radiologists. And ChatGPT answered that while AI technology is advancing rapidly in the field of healthcare, including radiology, it's very unlikely that AI would replace oral radiologists. AI can assist radiologists in interpretation of images more efficiently, accurately, and I will add here, quickly, faster, but the expertise and judgment of human being are still crucial in making complex diagnostic and treatment decisions. So oral radiologists are characterized by unique understanding of oral health and diseases that AI currently cannot replicate. I would underline the word currently, and I would also underline that ChatGPT gives me the answers on the basis of research of resources on the internet. So if we humans write on the internet that AI will not replace us, then ChatGPT will give me this answer. So what will happen, really? Well, Geoffrey Hinton, he got the Nobel Prize in 2024 in the field of physics for discoveries that enable machine learning with artificial neural networks. So that's why he's called the father of AI. And in 2016, Geoffrey Hinton said that radiologists would be obsolete in 5 years, so it would be in 2021. In 2015, Elon Musk said that self-driving cars would be available in just 2 years and replace regular cars. So in 2024, what have we got? We've got radiologists in regular cars driving to work in traffic. Of course, all these radiologists who still work in outpatient clinics and in hospitals who do not work in teleradiology from their own homes. But anyway, we are still here, we radiologists. And Charles Darwin said that it's not the strongest or the species that survives, not the most intelligent that survives, it's the one that is most adaptable to change. So I think that after listening to this lecture, you shouldn't draw a conclusion that it's not necessary to learn for the final in radiology because radiology will be replaced by AI. We would rather say